Lest you think all pumping circuits necessitate float switches, consider the ladder logic diagram coordinating the function of three motors: a motor-driven compressor, a type of pump, a motor-driven fan, and a motor-driven evaporator in an air conditioning unit. The first rung includes a normally open temperature switch, a normally closed pressure switch with a set value at the lowest pressure the system is intended to operate, called PS low, and a normally closed pressure switch with a set value at the highest pressure the system can safely operate, called PS high. The contactor coil of the compressor C and the overload contacts for the compressor, fan, and evaporator. Recall from our previous discussion of overload contacts that this is a series arrangement, and that an overload in any one of these three different devices would de-energize all three motors. Rung 2 is an auxiliary contact of the C contactor called C1 that serves as a holding contact. Rung 3 is the contactor coil of the fan, F, and rung 4 is the contactor coil of the evaporator, E. If the temperature switch detects a temperature above its set point, it initiates operation of all three rungs. Rung 3 and 4, governing the fan and evaporator, have no additional controlling logic, and the fan and evaporator primary contacts close. The fan and evaporator start fanning and evaporating as intended. The series arrangement of the two pressure switches in rung 1, however, basically keeps the compressor operational only between a certain range. If pressure is lower than the PS low set point, both PS low and PS high are in their deactivated normally closed state, and the compressor contactor coil C is energized. The primary C contactor would close, as would the auxiliary contact C1. Note as pressure rises, it will eventually surpass that of the PS low set point. PS low opens, however, the now closed C1 holding contact in parallel with it keeps the compressor contactor coil C energized until pressure reaches that of the PS high set point. When PS high opens, the compressor contactor coil C is de-energized. The primary C contacts open, as would the auxiliary contact C1. As pressure falls to the reset value of PS high recloses. Pressure continues to fall until it reaches the reset level of PS low, at which point PS low also recloses. The compressor is again energized, keeping pressure oscillating between the PS low and PS high values as intended. Note that as long as temperature switch 1 is closed by an ambient temperature in excess of its set point, the compressor stays inside an operational range, bouncing between low and high set points, and the fan and evaporator keep fanning and evaporating as intended. The coordinated activity of these three devices cools the space and keeps everyone happy. Lest you think all pumping applications are fully automatic in nature, consider a motor-driven pump supplying flow to an electrically controlled hydraulic system. Let's ignore the ladder logic governing the control of the hydraulic components at the top and focus our attention on the ladder logic governing the safe operation of the motor-driven pump. Notice this section of the ladder logic features a holding circuit with momentary contact push buttons followed by three devices: a normally closed pressure switch, a normally closed temperature switch, and a normally open float switch being held closed. Note the arrow modifier. Recall that all schematics are always drawn in their depowered state. The arrow modifier holding the normally open switch closed means that this system is intended to initiate operation with the float switch actuated. This means there should be hydraulic fluid in our reservoir. Consider the implication of these devices in series with one another and their intended function in this circuit. If the e-stop and all three automatic switches following the holding circuit and momentary contact manual push buttons are closed, the manual switches do exactly what they say. If an operator presses and releases start pump, the P contactor closes, and the P1 holding contact maintains this last asserted state. If an operator presses and releases stop pump, the P contactor opens and the P1 holding contact drops out. If, however, system pressure as indicated by the pressure switch, exceeds a given value, the normally closed pressure switch would open and de-energize the motor-driven pump and disable the operator from starting it until pressure dropped below the reset value. This electrical pressure switch, in effect, backs up the hydraulic pressure relief valve should the pressure relief valve fail to limit maximum working pressure. Similarly, if fluid temperature, as indicated by the temperature switch, exceeds a given value, the normally closed temperature switch would open and de-energize the motor-driven pump and disable the operator from starting it until the fluid cooled. The temperature switch prevents fluid degradation due to over-temperature conditions. Finally, if the fluid in the hydraulic reservoir ever dropped below the reset value of the normally open float switch being held closed, the float switch would return to its normally open deactivated state. The open float switch would de-energize the motor-driven pump and disable the operator from starting it until fluid is replenished. The float switch therefore prevents the hydraulic system from pseudocavitation by sucking in air from the depleted reservoir. The ladder logic controlling the motor-driven pump therefore serves several purposes. 1, it only runs the pump when an operator calls for it, and 2, it protects the system from overpressure and overtemperature events, as well as from low fluid levels. Notice, however, if an operator were to press and release start pump, and the pump didn't start, there could be several reasons why, and an operator could only guess at the reason. Is the e-stop open? The stop pump push button stuck open? The start pump push button not closing? The motor overloaded? The pressure too high? The temperature too high? Or is the fluid too low? Notice there's no feedback, and an operator is going to scratch their head and say, "Don't work," on their maintenance requests, giving you, the technician responsible for returning this pump to service, no clue as to what to expect. It is for this reason ladder logic can also be used to perform diagnostic services. Consider this ladder logic diagram offering rudimentary feedback about the state of this system. Note that the pressure switch, temperature switch, and float switch now utilize additionally mechanically interlocked switches that energize pilot lamps that give visible indications of the nature of the problem. Note the mechanically interlocked pair of switches turn off the pump and turn on the appropriate warning light. If system pressure is in excess of the set point, the normally closed side of the pressure switch opens, de-energizing the pump and disabling operation, and the normally open side of the pressure switch closes, energizing the pilot lamp that says overpressure. Similarly, if fluid temperature is in excess of the set point, the normally closed side of the temperature switch opens, de-energizing the pump and disabling operation, and the normally open side of the temperature switch closes, energizing the pilot lamp that says overtemp. Finally, if fluid level drops below the reset value of the float switch, neither side of the switch will be held in the activated state. The normally open side would reopen and de-energize the pump, and the normally closed side would reclose and energize the pilot lamp that says low fluid. Alternate methods exist that do not necessitate the use of mechanically interlocked switches. Consider this implementation, that rather than the pressure switch, temperature switch, and float switches directly inhibiting the P contactor coil from closing, 3 control relays and their associated contacts indirectly do so, as well as give visible indications of the nature of the problem. Note that the pressure switch, temperature switch, and float switch all selectively energize or de-energize an appropriate control relay coil upon closure. When energized, that particular control relay's associated contacts would change states. If PS1 detected high pressure, it would energize the pressure relay coil, PR. The associated PR1 contact would open and de-energize the P contactor coil. The associated PR2 contact would close and turn on the overpressure pilot lamp. If TS1 detected high fluid temperature, it would energize the temperature relay coil, TR. The associated TR1 contact would open and de-energize the P contactor coil. The associated TR2 contact would close and turn on the overtemperature pilot light. Finally, if float switch 1 registered unusually low fluid level in the reservoir, it would close and energize the fluid relay coil FR. The associated FR1 contact would open and de-energize the P contactor coil. The associated FR2 contact would close and turn on the low fluid pilot lamp. It may seem that this implementation uses more hardware than that of the mechanically interlocked switch pairs. However, realize hardwire relay-based ladder logic is being replaced with programmable logic controllers, PLCs, that can utilize programmed virtual elements to serve the purpose of physical relays. This implementation utilizing relays might be better suited for a PLC, since it would actually use less hardware, wiring, and 3 non-mechanically interlocked switches. We'll discuss PLCs and PLC programming in later lectures. Alright, this about wraps up our examination of various pumping circuits. Again, keep in mind at this point in your education, I am not asking you to design ladder logic diagrams. All I'm asking you to do is be able to interpret existing ladder logic diagrams and determine the response given various input conditions. My intention in this lecture was to serve as a guide for representative samples of ladder logic diagrams performing common recognizable industrial functions utilizing some of the concepts and devices we've thus far discussed. In conclusion, this lecture examines several different types of pumping circuits performing common industrial functions. We looked at a sump pumping circuit using a float switch at the bottom of a sump, a tank filling circuit using a float switch at the top of a tank, a pumping circuit designed to pump out a quantity of fluid using 2 float switches at different levels, a dual pumping system that coordinated the efforts of a primary and backup pump using 4 float switches and an alarm circuit, an air conditioner circuit coordinating the activity of a motor-driven compressor, fan, and evaporator, and finally, an operator-initiated hydraulic pumping circuit that disables the pump in the event of overpressure, overtemperature, low fluid, or overload conditions. We had a brief discussion of overloads common with each other, in series with each other, and in a cascading arrangement with each other. Finally, we examined 2 types of diagnostic circuits that both serve to turn off the pump and turn on an appropriate warning light, one utilizing mechanically interlocked switches, and the other utilizing control relays and associated contacts. Remember to review these concepts as often as you need to really drive it home. Imagine how well that will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.